Okay, let's continue. With the rest of stuff. So we defined conservative forces. Two examples that we frequently use are gravity and spring forces. Excuse me. And the reason we did this is simple. Because the work of these two forces do not depend on the path of motion, we can define them as potential energy, because similar to kinetic energy only depends on where the particle is. These two terms, half k x squared and mgy, only depend on the position. So if we define them as potential energy, right, we can consider them as gravitational potential energy and elastic potential energy, because these energy terms only depend on the position of particle, as I said, similar to what we had for kinetic. Now, if we consider the work of conservative forces as potential energy, we're going to consider mgy as gravitational potential energy and half k s squared as elastic potential energy. Again, your textbook uses V, capital V, for potential energy, which we also use it for velocity. So it might be confusing sometimes, but that's how it is. If you separate this, then you can say this is the same work energy principle. Initial kinetic energy, work of all external forces gives you final kinetic energy. However, we separate the work of conservative forces, which are these two, and the work of non-conservative forces, which is a friction force and any pulling and pushing and other external forces. Okay. Any question about this? So this is the same equation. We just separate conservative, non-conservative part of it. And now the conservative part, we can use it like delta VG, delta VE here. The non-conservative part, it remains as it is because it could be anything else. And T1 and T2 are the kinetic energy. Any question about this? And it may look confusing, but as we continue with this, so the work of conservative, we're going to get like V1 minus V2, change of potential energy. You substitute it there, then you get T1 plus V1 plus work of non-conservative is T2 plus V2. So it makes it nicer to understand if we consider the kinetic as and potential energy as overall mechanical energy of the system, then you can express this as the initial mechanical energy of the system plus work of all non-conservative forces gives you the final mechanical energy of the system. Make sense? So you could use this equation and you could use T1 plus U1 to T2 is the same. We just separate these terms. But something that makes it nice is this. Imagine you have a system that does not have any non-conservative force, which means this term does not exist. There's no friction, there's no pulling or pushing or any other force. If that's the case, you can simply say T1 plus V1 equals T2 plus V2. And we call this conservation of energy. Is it too much? Too quick? So Let me go to a slide and classify this because this is not very complicated, but you may get confused. So the principle of work and energy, the way we talked like 4 or 5 slides back, was this: T1 plus summation of U12 equals T2, right? We separate this as U12 non-conservative and U12 conservative. U12 conservative is like delta VE and delta VG, or you can simply call it delta V as change of potential energy. So if I simplify that, and delta V is going to be V1 minus V2. If I simplify that, T1 comes here, U12 non-conservative stays, then this part, you have V1 here. I'm going to get minus V2 to the other side. And then T2 comes here, right? That's what you get. T2 comes directly here, V2 comes here, V1 comes here, and that's what you get. Now, if this doesn't exist, then you can simply get T1 plus V1 equals T2 plus V2. Conservation of energy. That means the amount of mechanical energy you have going from point 1 to point 2 will be the same. Make sense? If you have a system of particles, you have more than one, you can get summation of T1 plus V1 equals summation of T2 plus V2. Remember, V is mgy plus half k s squared. I emphasize here one more time, S is the deformation of the spring and not its length. Okay, it's not the length, it's the deformation. Could be compressed or expanded, because this is S squared, or compress and expand, doesn't matter, it's just same. Any question? So practically, when there is no non-conservative force, as I said, the amount of mechanical energy of the system remains constant. If you have a system of particles, for the whole system of particles, that remains constant. That means the energy could increase in one particle and decrease in other particles. One spring could be extended more, gaining more energy. The particle could lose its kinetic energy. Things could go up and down. The gravitational energy changes. The combination of all of that will remain constant, right? Any question? Looks good. Now, with this concepts, let's go back and review this problem. When you solve this problem, what is the non-conservative force? What is the conservative force? Do we have any conservative force here?
Would that be at the moment the train hits the bumper?
Remember, conservative force is not about moment, is a type of force. The train hits the bumper is the beginning of the problem, right? As the bumper is compressed, it slows down the speed of the train car, right? So the kinetic energy of the car is absorbed by the spring. The question is this a conservative force or no?
No.
Why? Because when you say no, that means the work done by that spring depends on the path of motion, does it? Because when we integrated this, we still got k s cubed divided by 3 from 1 to 2, right? It is a nonlinear spring, but it's still conservative force because it doesn't matter how you get from beginning to the end. The work done by that spring is just S1 cube, S2 cube, the difference. Make sense? It is a nonlinear spring, but it's still conservative because the work it does doesn't depend on the path.
Okay.
Did it confuse you?
A little bit.
It's good to be confused because I want you guys to focus on the concept of conservative, right? Anytime you integrate a force over displacement, you get initial final. That means it doesn't depend. Here's the point. If, let's put it this way, if this car goes and compresses this bumper to some extent and bumper pushes back and becomes neutral, you see, the bumper compressed and then expanded again. At that moment that it expands, everything is the same. You don't lose energy, you don't do anything. That's not true with friction, right? You push something with friction, you do some work, you push it back, you still do some work.
If it is a conservative force, then how come we can use it in an integral?
We did it here because a conservative force is still a force. When you calculate its work, you still do the integral. The reason that, remember, this came from an integral, right?
Yes.
This also came from integral. So integration doesn't change the fact that it is conservative or not. What changes the fact is that if you go somewhere and go back, the system becomes like before, right? Or if you go
for
from
weight, if I was, say, 3 seconds ago, I was sitting right here, my weight would have still been 200 pounds. But if I go 3 seconds forward into the future while I'm still sitting here, or maybe 5 inches over, my weight is still 200 pounds.
That is not what makes the work of the weight conservative. what makes it conservative? Yeah, technically, because it's constant, right? Well, I think that's not a good example. Let's put it this way. Your weight is 200 pounds, and you sit there, no displacement, no nothing, no work done. Like I'm sitting here for 1.5 hours, there's no work done, right? If I go up and down, for example, if I go down to the first, I'm in the second floor in my house, right? If
Yeah.
I go to the first floor, it doesn't matter if I go through the stairs or drill a hole and fall completely down, right? I am here and the stairs go like this way and come back here. This is one path and I'm falling through the hole. This is the second path. The work of gravity is the same. It doesn't depend on the path. If I go to the roof and jump from the roof to the first floor, it's still from here to here. I don't know if you can see my hands. It's still from to here, here is the same work. That's what conservative means. It doesn't matter how you go. But
Okay.
friction, and here's the thing. I am sitting in my desk. I gave you 4-minute break. I went down the stairs and came back upstairs, sit the same. So I'm here, go down and come back. My overall displacement is how much?
0.
How much is the work of gravity? 0, right? But for the friction, when you push your fridge out of its position to the other side of the kitchen, you do some work. You push it back to the same point, you do some more work. You go from here, come back the same, the work is not 0. Does that make sense?
Mm-hmm.
That's the best way to understand it, because if the work of a conservative force depends on the position, if you go around and come back to your original position, the work should be 0. If that's 0, it's conservative. If it's not 0, that means it depends on the path. For this nonlinear spring, if you compress, if the car compressed it and then goes all the way down, and the work is good enough, the force of the spring is that pushes the car back, right? Then you come to the same point, car is going to have the same speed of 4 meters per second, and the spring has 0 deformation, and that makes it conservative. Right?
Okay.
Does it make sense?
Yeah.
Okay. So I have good news for you guys. If I'm going to scroll down the slides, this is 1, 2, 3, 4, and we're done with this chapter, believe it or not. Okay, this is relatively shorter chapter. And the good thing is, remember, the work energy creates one single equation. Unlike, normal and tangential and X, Y, Z, you have multiple equations. The work energy itself creates one equation. You may need more equations getting from kinematics or other stuff, but the work energy itself creates one scalar equation, so it's usually easier to solve. Now, I am going to go with this problem first. Okay? You know what? We may not be able to finish this. I'm going to cut it short here. You guys owe me 10 minutes, okay? Because I don't want to start a problem and rush quickly to finish. This is the first problem of this part. We cannot finish it in 10 minutes unless I rush it, so I don't want to do that. I'm going to stop the chapter here, the lecture, but you guys owe me 10 minutes. So if you go a few minutes over, we will even in another lecture. Is that okay? Okay. Now, a couple of reminders. The homework is due tonight, midnight, and we have a quiz covering chapter 13 on Wednesday. The same format. You guys come to this room maybe 5 minutes, 3-4 minutes early. I create a link. The link will be activated at 10 o'clock, and I give you a certain amount of time to solve the problem plus 5 minutes to scan it and submit it, okay? Any question about today's lecture? Did we go too quick? I think that the work energy, the beauty of work energy is just, it makes things simple, and the concepts are, straightforward and simpler than others. Okay, let me just stop sharing and get the screenshot of the class for the attendance. And I know some of you guys pop in and out, but I usually check it last time. So I remember we had like 14, now with 13, someone may have missed it. Anyway, so that's it for today. As I said before, you have questions, you email me, we meet on Zoom, I address your questions. Please make sure if you need help, you get it from me, not other. I'm okay if you guys are friend talk and discuss things together. That's a very nice thing to do. And you know, it helps you to understand the concept better. But when you solve the problems for homework, you should do it individually, okay? Okay, thank you all very much. I see you on Wednesday, and I'm going to post the video sometimes later today afternoon. Have a good rest of your day. Goodbye.